Hello everyone and welcome to today's class. Today we are going to talk about functions and invoking a function, calling a function. And we are going to check under the hood and learn what really happens when you invoke a function in the operating system, at the CPU level, in assembly code as well as in C code, etc. And why is that information valuable? Well, there are a lot of different things that happens when you invoke a function, and knowing those things will make you a better programmer. Okay, so in order to do this, I have installed a new VPS server that runs on a 32-bit CPU. And that's so it's going to make it a little bit easier for us to disassemble the programs. So let me begin by logging into my new server, like so. And I'm going to show you how to set up the environment. So I begin by logging into as the root user, and this is a Debian machine. So the commands might differ a little bit if you're running Red Hat or SUSE or something else. But if you are running Linux on a server, you probably already knows how to install packages. So basically it's the same. We're going to start by installing the C compiler. So I'll do apt-get update, and then I'm gonna install GCC with apt-get install. And we need a couple of things. I will install GCC and G++, that is the C++ compiler. I will also install make. It's a program that allows us to create small scripts that compiles our code. And we also need the header files, the standard C library. And they keep renaming this, but I think it should be libc dev. So without this, we can't really compile anything. Let's see if I got it right. No errors, that's always a good sign. And I have the GCC command. Okay, we also need to prepare our assembly environment. So I will install nasm, that's our assembler. And we need a linker, the ld command. We probably had this installed already, but in case we don't, or in case you don't, it's inside of the bin utils package. And in addition to that, we also need the GDB, the debugger, and we need objdump, which is a disassembler. So this time it went a little bit faster than last. I have replaced my faulty router. Okay, so now the environment is set up, and I'm also going to I log out from the root shell, but let me just show you one thing. If we just do objdump like on bin ls, we will get a lot of things that we are not interested in. Yeah, we need the -d as well, because it shows a lot of different things. Besides this, as you can see, this is not the assembly standard that we are used to. As you can see, there is a prefix in front of the register, right here and right here, and in front of regular values you can see a $sign, etc. This is the so-called AT&T assembly standard. The one we are using is called the Intel standard. So we need to add -big M Intel in order to get this standard. So that's one thing. We can also replace this -D with the entire command. So -- and then disassemble equals, and then we can say a specific function like this. Let's wait a little bit with that. But the point that I wanted to make is that the -big M we want all the time. So we can do alias. Let me just see one thing. We can do alias objdump equals objdump -big M Intel, like this. So if we do an objdump now on, for example, bin ls, I always forget this D, so let's put it in there as well. Okay, it works. Great. So then we can edit a file called bashrc with a dot in front of it. And we can put our alias here. That way it will always be accessible even if we log out. So objdump -big M Intel, no, big M Intel -big D, like this, and save. Okay, now everything is set up. Now I'm gonna start by creating a directory for all this, and I'm gonna create a C file. So let's call this one function.c, and we will just include the stdio, and let us create a function, two functions. We will create a void and we'll call it func1, and this function will call func2, and we will define func2 as well, and this function will just print something on the screen. Hello from func2, like this. And then we will create a main function which will just invoke func1. And return 0, like this. And I will also put in the function declarations. So void func2 void, and let's copy this down, and we do the same with func1. Okay, so a very simple C file. We have one function which is named func1, and that will call func2, and func2 will just print something on the screen just so it does something, and inside of main we will just call the first function. So this is because we want to compile this one, and then we want to disassemble it. So a disassembler, it takes a executable program file and it shows the assembly code, because everything is assembly or machine code rather in the end. So that's why you all should learn assembly language and learn it very well, because then you will have access to the source code basically for every program in the world, at least the assembly version of the source code. Okay, so let's compile this one and just name this A, so I will rename it function.c. We run it through GCC. Okay, have a typo on line 15. In main. Okay, so this should go away like this, and it compiles. And if we try to run this one, we get the message hello from func2. Okay, so let's dig into the assembly code for this function or program. So we run our objdump, which is prepared, so we just run the objdump command followed by a program file like this function. So we run it against the binary executable program file, not the source code. And we get some output. Let's check if we can use this disassemble equals main. There we go. Okay, so here's our main. Okay, it's a couple of instructions. We have a push and a move, and we have a call somewhere, and we have a call to func1, and then we move 0 into the EX, and we get out of the function. So basically these three lines is not related to the function call. This is just ending the main function in the program. So this call, that is obviously part of it, and this call, however, is not. That is because we are inside of the main. I think it's better to show one of the functions instead of main, because that will be a little bit cleaner. Main is a little bit special because it's the main program function. But if we do the same with func1, for example, that should give us a little bit less input. Okay, we still get this weird call. Where does it go? 11E8. 11E8. So it basically jumps to 11. Where was it? 11E8. Is it possible to do disassemble 11E8? No. We could run it through GDB. Sure, why not? So this is the GNU debugger. We can use this program to debug our code and check values of registers and part of the memory and step through our lines of code, etc. But I want just to disassemble func1. Disassemble func1. Here we go. Oh, I don't remember all this color. That's a bit annoying. Anyhow, so this call here, it's still to 11E8. We can do, let's try disassemble 11E8, see what happens. No. But we can use the X command. The X command is used for checking what's inside a specific memory address or symbol. So we can do X and 11E8, for example, but that won't show us all that much. However, okay, let's do the whole 32-bit register. However, if we add a slash afterwards, then we can give more information about what we're looking for. We can, for example, do bx to get a byte of hexadecimal characters. We can do s to get a string, but I want to get an instruction, so I will do x/i. And then I paste in 11E8. Okay, so this is the register. This is the instruction, rather. So get PC thunk AX. Move ESP EX. Okay, so it basically just moves something off the stack towards the EX register. Maybe some kind of optimization or something like that. So let's not worry too much about this. I think we should focus our energy on the middle part. So, and this too, though. But for the call is the most important one. That's what actually calls the function and jumps over to that instruction where the function is. And this stuff with regards to the ESP, that's the stack pointer. This is preparing the stack. We need to kind of emulate how the stack looks like for each and every function in order to make those variables local. So now I think it's time to go over to a little bit of assembly code, and we're going to try out how we may call a function. We'll start with the easiest possible way, and we'll work our way up to this, so we know why we need the different parts of it. Okay, so I will create a new file which I will call what should we call this one? Let's call it call. So call.asm, and the bits will be 32. We will have a global exported symbol called start. We will have a section called data and a section called text. And as you remember, the data segment is what it sounds like. The data segment, that's where we keep our variables and our data. And the text segment is all the instructions, the assembly instructions. So this is where we will start our program, and we will make this quite easy. First of all, I just want a couple of instructions so this part of the code does something, and I will zero out a couple of registers. So into EX I will put a 0 byte, or a 0 double word rather, and I will paste this a couple of times, and I will do the same for EBX, ECX, EDX. And let's put a nope. And a nope is a no operation. That is an instruction that just goes to the next CPU cycle without really doing anything. Okay, so now we have a couple of instructions. Now I want to create a function, a very basic function that prints a static text on the screen. So let's begin by creating a label called str for string, and I will just put something like hello, and after that we will have a 0. No, we will have a new line, and then a 0 byte, like this. And we also need to have an address. No, and a size. So let's put it here as well as a variable. So str size, and that should not be a byte. We did dB here. The B is for 1 byte, so it takes 1 byte at a time. But this should be the entire register size, so that's 32 bits. And that's why we do D, I think, double word. And let's just put a 0 here. for now anyway. Okay. Or let's put the real one instead. Okay, so the size of this string is hello, it's 5, and then a new line, and 0 byte doesn't count, so we'll put 6 into this part of the memory. Okay, so we will call our function print, so I'll just do print like this. And if you watch the last episode, you know how to print something. What we do is into EX we put the value 4, and that's the fourth system call, which is write. And into EBX we'll put a 1, and that's for the standard output. Into ECX we should put the string, or the address to the string. So we replace this by the label str. But how do we do with the last register, the EDX register? We want to put the actual size of the string, the length of the string, and we have that here inside of the str size. But if we were to do like this, str size, what do we put inside of the EDX register? Well, it's not the 6, it's the address that this str size points to. And that's no trouble in the case of the string, because it expects a pointer there. But as this third argument, it wants the actual primitive value. So how do we do this? How do we, if we have a label or a memory address, how do we go into that address and grab a specific value? Well, we can do like this. We can utilize another register, for example, EDX, EX, EVX, ECX, EDX, and we should, wait a minute, let me just check real quick. If we do GDB on the function, and we put a breakpoint at start, and we run it. If we do IR, that's the command info registers, we will get information about all the registers. So these are the names of the different registers. These are the values. So we've used EX, ECX, EBX, EDX. We don't want to use the ESP because that's a stack pointer. The EBP is the saved stack pointer. The ESI, that one we can use, because we need a temporary register to put the address. So let's put into the ESI register, we put the address of str size, and into the EDX we put ESI. So we copy from ESI to EDX, but we don't just put ESI like this, because then we would do the same thing. We would copy the address. Instead, we put this into brackets. So this means that we are not copying the contents of the ESI register. We are using that as a pointer, as a memory address, and we grab the actual value that it points to. And that's what we put into the EDX register. And then we will just do the interrupt like this. Okay, so now we have our first print function done. And how do we call this one? Well, let's say somewhere in the middle of all these instructions, we will just use the jump instruction. So we jump towards print. That means that we are changing the instruction pointer, so we will evaluate this instruction next. So we jump towards it. And that should work, right? So let's just create an exit as well. And here we will just do move into EX a 1 and move into EBX. We can do it like this. XOR EBX, EBX. That means that we run an XOR operation with EBX against EBX, and that always results in zeroing out EBX. So this is a more effective way of putting a 0 inside of a register, because the move might be kind of expensive CPU-wise. And then we will do an interrupt like this. So we will quit with an exit 0. Okay, we say this one, we do NASM, and before we did ELF64, and that's perhaps what you should do if you're running a 64-bit system. But now I am not, I'm running a 32-bit system. So I will just do ELF this time. And then we will do call.asm, which should create the .o, and then we'll link it by ld call o -o and call, like this. And we run the program, and it prints out hello on the screen. No problem there. But the program exited directly afterwards. And if we go to our code, let me do a one-liner out of this, by the way. So we do the NASM, and if that succeeds, we will do ld call.o-o call, like this. So we save a little bit of time. Now I will go back to the code, call.asm, because, okay, it works. We are jumping to this function, but we don't have any way to go back. So we jump to it, but then what? We still need to go back somehow. And how do we do that? Well, we need to have the address of the, when we do the jump, we want to go back here, right? After the function has returned. So we need to get the memory address of this next instruction. And as I mentioned before, that is saved into the EIP register that always points to the next instruction. But where do we save that? We need to put it somewhere that we can use it later on inside of this function. Well, let's use the data segment just like before. So we will create a label called return address, and we will not put anything. We could do like this, that we put a whole 32 bits 0 like this, and that is all well and perfectly fine. But we don't really need to put anything here. What we want to do is reserve that space so we can put something there at runtime. And there is an instruction, instead of DD, we may use resd. So we reserve 32 bits. Like this. This means that we reserve 1 unit of 32 bits. And if we wanted, for example, 16 bytes, we could do resd2 or resb16, for example. So that would be 16 bytes of data that we reserve space for. Okay, but resd1 should be fine. And before we do this jump, let's move into ESI the address of the return address, like this. And let's see what happens if we just move into the contents of ESI, that is the return address on the data segment, and we will put the EIP. However, when we execute this instruction will be what the EIP points towards. So if we jump to that, it will be an endless loop. So we need to put the EIP plus the size of this instruction. So how big is this? It's quite easy to check. Yeah, let's do an obj dump on this one after we have saved. So let's save this and let's do an asm. What did it say? Warning, uninitialized space declared in non-B. Okay, it wants it in the BSS section, but that's really not error symbol EIP not defined. So we don't have access to the instruction pointer. I think there is an assembler, an asm macro that we can use to grab the current instructions address, What if we, instead of EIP, were to put a $sign here? Error operation size not specified, okay? When we don't specify a size, we can do move byte and something that will move 1 byte of data. But if we don't do that, then the assembler will interpret from the argument. So in some cases, like in these cases, we move a 0 into a 32-bit register, for example. ECX is a 32-bit register. So then it knows that it's a double word. So this instruction is really D word. But a double word is 32 bits, by the way. But it doesn't seem that it's able to figure that out in this case. So let's put the D word here, like this. Let me try again. Okay, the warning is still there, but it looks like it went through. Let's do an objdump on our call. And we are inside of start. So let's add -- disassemble equals start. And here we just get the start. Very nifty. Okay, so here is the move of the D word, and we move from this memory address that's right. So into the contents of ESI, we move this address. Okay, so it ends in 9010, and 9010 is this exact same instruction. So we can't really use that and return to this one, because then we would do an endless loop again. Instead, we want it to point towards the next one after the jump. So it should be 9018. So let's add 8 to the calculation. So instead of just $sign here, we should be able to do $sign plus 8. Let's try it again. Okay, so this time it's 9018, and 9018 is the correct. No, it's jump. Oh, it's the right one. So this is the instruction, the next instruction after the jump. This is where we want to return to. Okay, so it seems to be working. Let's go back and finish this off. So call.asm. So we put the address into the ESI and then we use it to write to this part of the data segment. Great. And then we jump to our print. We do the whole print operation, and then what? If we don't put anything here, we will do the exit right after. And in this specific case, that's no problem because it exits and we want to exit. But what if we wanted to call this function twice? So in that case, we would take these 3 and do them twice, like this. No, like this. Okay, so would this work? What happens if we do this at the current time? We want it to print the message twice and then exit. Let's see what happens. It just printed once. And it's important that you understand why. Because we have the same instructions. We jump towards print, we jump towards print. But the print doesn't jump back. We execute the print instruction and then we don't do anything, which means it will continue on to the exit function and exit the program. Okay, so how do we return to our how do we return to the function call, basically? Well, on the data segment, we did save the address, the return address. So we need to access that. Let's once again utilize the ESI register temporarily. And into ESI, we will move the return address like this. And then we will just jump back into it like this. So in ESI, we put the return address, and ESI with brackets around will be the actual return address, and jumping towards it would, in the first case, go here to the move instruction. Let's save and let's assemble the code and run it. Okay, interesting. We do get an infinite loop this time. And why is that? So first we jump to the print, then we move back towards this instruction, then we do the same thing once again, and we jump to print. Sure enough, and what if we were to do the same with exit? So we put the return address, which is really not necessary, but let's do it anyway. And then we will jump to exit. and we run NASM, and we run our code. Okay, this time it works. So we have created our own way of calling functions. But how does that correspond to how it's done for real? Let's go back to the code. Basically, it works the same way. It won't save the return address in the data segment, so we can remove this right here, and we can remove that part of the code. So those two, and those two, and those two. And let's change the jumps to call instead. And what is the difference? Well, basically it's the same thing. It jumps to another part of your program, but call does something additionally. What it does is it pushes the EIP to the stack. So it saves the return address on the stack when we do call, and then it jumps. So we can remove that part of the code, that's this one. And how do we return from the function then? Well, there is one instruction, which is just return. So call will push the return address from EIP to the stack, save it in memory. Then it will jump to the print, and it runs through all the code in the function, and then it returns from the function. We can add a return here as well, but since this exits the program, it's not really necessary, but it looks better. Okay, so if we have done this correctly, then we don't need anything else. If we run this code, it should print the message twice and then exit. Let's see if it holds up. It compiles, no warning. And if we run call, it prints the hello twice, and then it exits out. Okay, so now we have gone through everything related to calling the function, returning from the function, and handling the return address. I hope you enjoyed it. Don't forget to subscribe so you know when the next episode airs, and to get more content like this. Thanks for watching, and thanks for today.